Hello, my name is Akshat Tangsale, and you're watching the pre-lecture video for week 4 of the unit Material Energy Balances. Today I will recap what was covered in week 3 and then talk about what is coming up in week 4. So in week 3 we talked about multi-unit operations and material balance around those operations. In particular, we looked at recycle, bypass and purge. When combining multiple units in a process, you often end up getting mixing points and splitting points. These are special cases where material balance needs to be done, and there's a very simple rule around doing mass balance on these mixing and splitting points. So when doing material balance on a mixing point, you will end up having three different compositions for the three streams. So in this example, you have A, B combining to make C. A and B will typically have different compositions, and they will end up mixing and giving a third composition. So all the three streams in this example will have different composition. Whereas when it comes to splitting points, in this example, A is splitting into B and C. All the three streams will have the same composition. We then looked at material balance on a reactive system, and then we defined a few new terms like fractional excess, which is the amount a reactant is in excess over its stoichiometric proportion. And we defined fractional conversion as the amount a material has reacted divided by the amount a material was fed, both in terms of moles. We defined yield, which is the amount a desirable product is made divided by the amount a desirable product would have made if the reaction proceeded to 100% and no side reaction took place. Whereas we define selectivity as the amount a desirable product is made divided by the amount by which the undesired products are made. We defined some material balance around reactive process using molecular balance. Now, we did not look at any worked example on that because I do not recommend you doing material balance using mole balance. It's much better to do extent of reaction calculation or atomic balance calculation, which I will cover in week 4. On the topic of extent of reaction, I have a few tips. So first we will look at what is extent of reaction again. So we simply define extent of reaction as the amount of moles a reaction has proceeded by. The units of extent of reaction can be both in terms of moles for a batch system, or it can be moles per second or moles per hour for a flow system. The formula for extent of reaction is moles of a component in minus moles of that component out divided by the absolute value of the stoichiometric coefficient of that component. But sometimes you may not know the moles of a component coming out. Instead, a conversion value may be given to you. So using the conversion value, you can calculate moles coming out. For example, if a question says moles of a reactant going in is 100 and 50% of it is reacted, then 50 moles will be coming out. So now you know both moles in and out, and you can calculate the extent of reaction from the conversion value. Likewise, you can calculate extent of reaction from the yield given in the problem. Now, although we looked at calculating extent of reactions for multiple reaction problem, we will look at an alternative, which is atomic balance calculation, which is my preferred way of doing a multiple reaction problem. So for now, I will leave it at that, and we will look at atom balance when we go to week 4. So let's look at what is coming up in week 4. So next week we will finish chapter 4. I have been running a little behind schedule. I should have by now finished chapter 4, but I thought it was important for me to spend a lot of time because this is the foundation chapter of material balances. So after completing the atom balance problems, We will look at special case of reactions, which is combustion reaction, and then I will spend some time on showing you flow sheeting options in Microsoft Visio. Then we will look at chapter 5, which is mainly a theory-based chapter. We will cover equations of state for non-ideal gases system. In fact, first we need to define what is ideal gas, and then we look at how to deal with non-ideal scenarios. We won't be doing any problem solution on this chapter, but you will apply the principles learned in this in HYSYS tutorial. So that is all from me for now, and I'll see you in the lecture next week. Bye bye.